Hi to everyone, myself Dr. Dhananjay Rao, working as assistant professor in the Department of Chemistry. Today I am going to teach about Bakelite synthesis and its properties. Today I am going to teach Bakelite synthesis and its properties. See, in this video I am going to cover these are the topics. Thermosetting resin. What is thermosetting resin? And Bakelite synthesis. How we can prepare Bakelite and Bakelite polymer, and what are the properties of Bakelite and the applications of the Bakelite. In this video, I am going to cover these topics. What are the thermosetting resin? What is the thermosetting resin? And how we can prepare the Bakelite polymer, and properties of Bakelite polymer and applications of Bakelite polymer. See, before going to this, you should know about thermoplastic or thermosetting plastics or thermosets. Before going to this, I am going to tell about thermosetting plastics or thermosets. See, the thermosetting plastics get hardened on heating, and once hardened, they cannot be softened again. What is thermosetting or thermoset? The thermosetting plastics get hardened on heating. On heating, the thermosetting plastics getting hardness, and once hardened, they cannot be softened. Once hardened, they cannot be softened again. That is called thermosetting plastics or thermosets. What is the definition for thermosetting plastics or thermosets? See, the thermosetting plastics are getting hardened on heating, and once hardened they cannot be softened again. Those are called thermosetting plastics. See, the thermosetting plastics are prepared by condensation polymerization. How we can prepare thermosetting resins? The thermosetting plastics are prepared by using condensation polymerization. Okay, the various polymer chains are held together by strong covalent bond called crosslinks. In this thermoplastics, different polymer chains are present. Those are held together by strong covalent bonds. Okay, various polymer chains are held together by strong covalent bonds in the thermosetting plastics. They are almost insoluble in organic solvents. The thermosetting plastics are insoluble in organic solvents. Example for thermosetting plastics are Bakelite or polyesters. See, this is the thermosetting plastic. See, this is one chain and this is one chain. These two chains are held together by strong covalent bonds. Okay, these two chains are multiple chains present in the thermosetting plastics are held together by strong covalent bonds. What is the definition for thermosetting plastic? The thermosetting plastics get hardened on heating, and once hardened, they cannot be softened again. They cannot be softened again. Those polymers are called thermosettings. Polymers are thermosettings plastics. The thermosetting plastics are prepared by condensation polymerization. How we can prepare? The thermosetting plastics are prepared by condensation polymerization. Various polymers chains present in these thermosetting plastics are held together by strong covalent bonds. These are almost insoluble in organic solvent. The thermosetting plastics are insoluble in almost all organic solvents. These are the example. What are those? Bakelite and polyesters are the example for thermosetting plastics or thermosets. The bakelite or phenolic resin. See, the bakelite or phenolic resins are example for the thermosetting plastics. Okay, the bakelite or phenolic resin. The bakelite other name is phenolic resin. These are the example for the thermosetting plastic. See, it is obtained by the condensation polymerization of phenol and formaldehyde in the presence of acid or alkali catalyst. How we can prepare bakelite? The bakelite is obtained from the simple condensation polymerization. We can prepare bakelite by using the condensation polymerization. What are these starting materials? See, the condensation polymerization between phenol and formaldehyde. Thus, the condensation reaction between the phenol and formaldehyde in presence of the catalyst. What are the catalysts? Acid or alkali. Acid or base. If you use the catalyst, then we can prepare from bakelite from the phenol and formaldehyde monomers. Okay, we can prepare bakelite polymers by using this phenol and formaldehyde in presence of acid or basic catalyst. It produces bakelite or phenolic resin. The bakelite or phenolic resins are prepared by simple condensation polymerization. See, what are the starting material in the bakelite synthesis? The phenol, formaldehyde or acid or basic catalyst. Okay, these are the starting materials for the synthesis of the bakelite or phenolic resin. See, the preparation. The reaction involves the following three steps. The reaction of Bakelite, the Bakelite synthesis involves 3 steps of reactions. See, in that first step, see, the first step is the reaction between the phenol and formaldehyde. In the first step, the reaction between the phenol and formaldehyde. It forms a orthohydroxyl methylphenol or para-hydroxy methylphenol. When this is the phenol, okay, this is the phenol and reaction with formaldehyde. This is the formaldehyde in acid or basic condition. What are these forms? See, the orthohydroxy methylphenol or para-hydroxy methylphenol. See, the phenol reacts with formaldehyde in presence of acid or basic medium. It produces orthohydroxy methylphenol or para-hydroxy methylphenol. These two things found in the first step. See, the methylphenol, see, hydroxyphenol, okay, OH, this phenol, the OH functional group acts as the ortho-para directing group. Okay, the OH group acts as ortho-para directing group. So, because of this, the negative charge existed at ortho and para positions. Okay, this OH, the OH function, because of OH function group present on the phenol, it acts as a ortho and para directing groups. So, the negative charge present at ortho and para positions. So, at ortho and para positions, excess negative charge present. Hence, these acts as a nucleophile. Okay, these acts as a nucleophile. The formaldehyde contain C-double-bond-O functional group. So, here there is in presence of acid or basic medium, there is strong electrophile generation takes place. This nucleophile at ortho and para, these are reacts with this electrophile. These nucleophiles at ortho and para positions reacts with the electrophile and forms a ortho hydroxy methylphenol and para hydroxy methylphenol. See, in the first step, what happens? In the first step, the reaction between phenol and formaldehyde in presence of acid or basic medium, it produces orthohydroxy methylphenol or para-hydroxy methylphenol. Okay, the orthohydroxy methylphenol and para-hydroxy methylphenol. In this, the phenol, the OH group is present. That acts as a ortho and para directing groups. Hence, that ortho and para positions nucleophilic charge generates. Okay, these nucleophiles reacts with the formaldehyde in presence of acid basic medium. The formaldehyde forms strong electrophile. These nucleophiles at ortho and para positions react with this electrophile formaldehyde and forms a two things. One is orthohydroxy methylphenol and para-hydroxy methylphenol. In the first step, these two are formation taking place. In the step 2, so see step 2, when orthohydroxy methylphenol are heated with excess phenol in presence of acid catalyst to form novalogs. What happens in step 2? In the first step, two things are formed. One is orthohydroxy methylphenol and para-hydroxy methylphenol. In this, one orthohydroxy methylphenol and treated with excess of phenol. This orthohydroxy methylphenol treated with excess of phenol. Okay, excess of phenol, it produces novolog in presence of acid or basic medium. In presence of acid or basic medium, what happens? The orthohydroxy methylphenol. This is orthohydroxy methylphenol and reacts with phenol, excess phenol in presence of acid or basic medium. What it forms? It forms novolog. It forms novolog. See, there is here one hydrogen is there. Okay, this CH2OH and this hydrogen eliminated as minus H2O. There is a condensation takes place between this phenol and orthohydroxy methylphenol. There is elimination of water molecule. Form there is a bridge between two phenol rings. That is CH2 bridge between two phenol rings. If you add the again it reacts with this orthohydroxy methylphenol. What happens? Again here one hydrogen is there and H and OH minus H2O. Water elimination takes place, forms this linear chain. Okay, this linear chain that is called novolog. The novolog is a linear branch of polymer. The novolog is a linear branch polymer. In between two phenol rings, there is a methyl bridge present. In the novolog, there is a methyl group. There is a methyl functional group present between two phenolic functional groups. So, this is called novolog. In first step, what happened? In first step, the phenol reacts with formaldehyde in presence of acid or basic medium. It produces orthohydroxy methylphenol and para-hydroxy methylphenol. In this orthohydroxy methylphenol again reacts with excess of phenol. Okay, excess of phenol in presence of acid or basic medium. It produces novolog. Okay, it produces novolog. See, in this orthohydroxy methylphenol, the OH group, and this hydrogenate phenol reacts together eliminated as a water, and there is a bridge formation between these two phenol rings. The bridge is methyl functional group. The methyl functional group is acts as a bridge between these two phenolic rings. That is called Novolac. Novolac is a linear branch polymer. Novolac is a linear branch polymer. This is formed in the second step. See, in the step 3, the Novolac on heating with excess amount of formaldehyde. In the second step, Novolac formation takes place, and this Novolac again heating with the excess amount of formaldehyde undergoes cross linkage to form insoluble solid mass called Bakelite. Okay, how we can prepare Bakelite from these Novolacs? The Novolac on heating with an excess amount of formaldehyde. Okay, it forms cross linkage, forms a infusible solid mass called Bakelite. How we can produce Bakelite? When Novolac reacts with excess amount of formaldehyde, okay, on heating it produces Bakelite. Okay, see how we can prepare Bakelite? The Bakelite prepared by 3 steps. In first step, what happened? In first step, phenol, okay, phenol reacts with formaldehyde, HC11OH, okay, formaldehyde, it produces orthohydroxy methyl, okay, orthohydroxy methyl phenol and parahydroxy methyl phenol. Parahydroxy methyl phenol. In first step, what happened? The phenol reacts with formaldehyde in presence of acid at basic medium. It produces orthohydroxy methyl phenol and parahydroxy methyl phenol in the first step. In second step, what happened? In second step, orthohydroxy. In second step, orthohydroxy methyl phenol, okay, reacts with excess amount of phenol. Okay, excess amount of phenol. It forms Novolac. Novolac. This is the structure of Novolac. Linear branch chain formed. That is Novolac. How we can form Novolac? The Novolac reacts with, the phenol reacts with excess amount of orthohydroxy methyl phenol. Okay, excess amount of phenol reacts with orthohydroxy methyl phenol. Under heating, it forms linear branch chain, that is called Novolac. Okay, that is called Novolac. In third step, what happens? This Novolac reacts with excess amount of formaldehyde. The Novolac reacts with excess amount of formaldehyde, and the linear linkages, the linear cross links are formed. Okay, that is called Bakelite. That is called Bakelite. See the structure of Bakelite. This is the structure of Bakelite. This is the structure of Bakelite. See the orthohydroxy methyl phenol. Orthohydroxy methyl phenol undergo polymerization. It forms Novolac. First it forms Novolac. Okay, it forms Novolac. That is a linear polymer. The linear polymer Novolac again reacts with excess amount of formaldehyde under heating condition. Under heating condition, what happens? This the Bakelite, the cross-linked polymer formed. The cross-linked polymer, that is called Bakelite, formed from the Novolac. Okay. See how we can write the Novolac structure. Okay. First write the Bakelite structure. First we have to write the Novolac structure. OH, CH2, again OH and CH2, again OH. This is the structure of Novolac. Again we have to write in this reverse direction. Okay, reverse direction we have to write the Novolac structure. See, OH, CH2, again OH, CH2 and again OH. First we have to write Novolac structure. Again reverse this Novolac structure and write again in the down bottom. Okay, in between these two benzene rings, write a, keep a methyl bridge. In between two phenyl rings, you have to keep a methyl bridge and leave one phenyl rings. Again keep a CH2 bridge between two phenyl rings. This is the structure of Bakelite. We can write the structure of Bakelite from the Novolac like this. Okay. These are the properties of the Bakelite. See, it is a thermosetting polymer that cannot be that cannot be reused or remolded. See, it is a thermosetting polymer that cannot be reused or remolded. The Bakelite is a thermosetting polymer. Okay, it will be formed from the condensation polymerization, and it cannot be reused. It cannot be reused and remolded. It cannot be remolded. Bakelite is a resistant to acids, salts, and most of the organic solvents. The bakelite is a resistant to acids, salts, and most organic solvents. Okay, but it is attacked by alkalis because of the presence of OH groups. See the structure of the bakelite. It contains large number of OH functional groups. Okay, large number of OH functional groups. Hence, these are soluble in alkali media. The OH reacts with NaOH or any type of alkali. It forms O minus Na plus type of structure. So, all the bakelite, okay, all the bakelite molecules are soluble in alkali medium. That is okay. But is attacked by the alkali because of the presence of OH groups. Because of the OH functional groups, bakelite polymer is soluble in alkali medium. It possesses excellent electrical insulating properties. The bakelite possesses excellent electrical insulating properties. See, these are the uses of bakelite. See, what are the uses of bakelite? Bakelite is used as a plywood lamination and grinding wheel, etc. Bakelite is used as a plywood lamination and grinding wheel, etc. It is also widely used in paints and varnishes. It can be used as paints and varnishes. Okay. It is used for making electrical insulator parts like plugs, switches, heaters, handles, etc. By using bakelite polymer, we can prepare plugs, switches, heaters, and handles, etc. It is used for making combos, phonograph records. By using bakelite polymer, we can prepare combos, phonograph records, and handles of various utensils. Handles of various utensils we can prepare by using this bakelite polymer. See, in this video, what I have covered, thermosetting plastics or thermosets. What is the thermosetting plastic? Thermosetting plastic gets hardened on heating, and by cooling, what happens? It cannot be softened again. Okay, they cannot be softened again. The thermosetting plastics are get hardened on heating, and once they are hardened, they cannot be softened again. Those are called thermosetting plastics. The thermosetting plastics are prepared by simple condensation polymerization. How we can prepare thermosetting plastic? The thermosetting plastics can be prepared by using condensation polymerization. In between the thermosetting plastics, the between two linear charges, there is a covalent bond present. Okay, the strong covalent bond is present. The example for the thermosetting plastics are bakelite and polyesters. These are not soluble in organic solvents. See how we can prepare bakelite. Bakelite is the example for the thermosetting plastic and condensation polymerization. Okay, simple. The bakelite is prepared by using phenol or formaldehyde resin. The catalyst is acid or basic mediums. The bakelite is prepared by using 3 steps. In the first step, what happened? The phenol reacts with formaldehyde in presence of acid or basic medium. It produces 2 products. One is orthohydroxymethyl phenol and second one is para-hydroxymethyl phenol. In the first step, 2 products are found. First one is orthohydroxymethyl phenol. The second one is para-hydroxymethyl phenol. In the second step, what happened? There is a reaction between orthohydroxymethyl phenol in presence of excess amount of phenol. Okay, there is elimination of water molecule takes place. It forms a linear chain polymer, that is Novolog. The Novolog is formed by using the starting materials. The orthohydroxymethyl phenol reacts with excess amount of phenol. Then in these conditions, what happened? There is a linear polymer formed, that is Novolog. The second step, Novolog formation takes place. The third step, the Novolog reacts with excess amount of formaldehyde in hot heat condition. What happens? This forms a bakelite polymer. This is the structure of bakelite. Okay. The Novolog on heating with excess amount of formaldehyde. Okay. Undergo cross linkaging and form a infusible solid mass called bakelite. Okay. This is the structure of bakelite. These are the properties of the bakelite. See, the bakelite is a thermosetting polymer. It cannot be reused or remolded. The bakelite is resistant to the acid, salts, and almost organic solvents, but it is soluble in alkali mediums because of the OH functional group present on the bakelite structure. It possesses excellent electrical insulating properties. The bakelite possesses excellent electrical insulating properties. See, uses of bakelite. See, bakelite is used as a plywood lamination and grinding wheel, etc. Bakelite is used for a plywood lamination and grinding wheel, etc. It is also widely used in paints and varnishes. It can be also used for paints and varnishes. It is used for making electrical insulators parts like plugs, switches, handles, heater handles. Okay, by using bakelite we can prepare these plugs, switches and heater handles and etc. It is used for making combos, phonograph pickers, handles of various utensils. By using bakelite we can prepare combos, phonograph pickers and handles of various utensils. These are the uses and properties of the bakelite. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.